Okay, hi. Sorry that this took a bit longer than expected. I for some reason got the flu while staying at Denise's place by leaving my window open, so I had a slight fever for a few days. But now I'm relatively better, so yeah, now you get your cool proof. Also, I was very happy to hear from you. Okay, I'll prove a slightly different statement, which implies this statement I showed you, just because proving the actual statement I showed you is annoying and technical and not very fun. Okay. Though also doable. It's like maybe what? With the setup, maybe 1.5 hour proof. Okay. So what are we gonna prove? So we have our space, capital X, compact metric. Meaning it, let's say it behaves like 0, 1 to the n in Rn. So just like a cube in Rn with a cube containing its boundary. So any continuous function on here would be bounded, for example. So it has a maximum. So right, for example, just Rn itself wouldn't satisfy that because, for example, the identity goes up in an infinitely high. Or yeah, if you just have, for example, the open interval 0, 1 in R, so in the real numbers, then that wouldn't satisfy that either, because you could have 1 over x, which is as a function from 0 to 1 to the real numbers continuous, but it goes up infinitely high as you go to 0. Okay. Cool. Then we have f in L2. What that means is f is integrable with meaning that f squared is integrable and smaller than infinity. There's just like a small condition that this integral even makes sense, but as long as f is not ridiculously ugly, this integral will make sense. And what we're saying is the square of this integral of the function is, the integral of the square of the function is defined and it's smaller than infinity. Okay. What I mean by d mu here is that mu is our measure on the space. So this is this function that maps subsets of x to non-negative real numbers in such a way that the measure of the empty set is 0, the measure of the entire set is 1. So we call the evaluation of this function the measure. So this is the measure. And the measure of a set is, okay, I think that makes sense. And if you have a1, an in x, then disjoint in x, so pairwise empty intersection, and they don't even need to be finite. You can even have just countably many, right? So an amount where you would hit every one of them if you just start counting 1, 2, 3, 4, 5, 6, 7. So mathematically, there exists a bijection from the natural numbers to the set of sets for which I'm making this claim. Okay, then the measure of the union is equal to the sum of the measures. There's a small subtlety here. Actually, we only want this for some set which is a bit smaller than the power set of x. So it's not, it can't be arbitrary disjoint subsets. The subsets need to be not ridiculously ugly, because otherwise, like for example, as I think I told you, like you wouldn't find a measure which is well defined on all of the real numbers, translation invariant, and has mu of I'm being silly, AB, so that the measure of the closed interval from A to B is B minus A for B bigger equal A. And like to get something like this, you need to restrict yourself to a quite large subset of the set of all subsets of the real numbers. Okay. Good. So what do we now claim? So yeah, we have this measure mu. We call it a probability measure because the measure of the entire set is 1. Then we have this function which is square integrable, and we have some function t going from x to x. Let's just say bijective and measurable. Measurable also doesn't need to concern you too much. It's like a continuous would be a completely fine, way weaker replacement. Basically just means it plays nicely with this measure, and it doesn't completely screw up our measure. Like essentially just that because the measure is we only really want to look at the measures for sets with which it plays nicely. We want that pre-images of open sets under this map are still measurable, so still behave nicely with this map. But this is more like, a cool subtlety and an important subtlety, but before taking this course, you would take an entire semester course on how to make this all play nice. And in the end, you again kind of treat it like a black box, but then you understand like why it's necessary to be a bit annoying and technical about it. Okay. But bijective and continuous would be more than enough. Okay. So the original claim I showed you was that 1 over n k equals 0 to n minus 1 of f composed with t to the k of x converges to the integral of f d mu for almost all x in x, meaning that the set of exceptions has measure 0. Okay, so what we're now going to prove is slightly weaker, namely that okay, it's not weak, it's a different statement. And it applies a weaker version of the statement. But it's less useful, in my opinion. But it's cool and it's easier to prove, and it's nicer to prove, and it was proved by John von Neumann, so, you know. Okay. Quickly, perhaps one input. What does this even mean? Because we're not... mu might be any measure. It turns out you can define the integral for measures other than the thing which you would be comfortable with, which is like the dx would just mean that the measure, like if you would write it down in a classical calculus 1 style, then this would just be the same as mu being this measure that assigns to the closed interval AB the measure B minus A. But you could, for example, have, let's say, a measure that assigns 1 if and only if, let's say, the number 1 is contained. And 0 otherwise. And then the integral of the function would just be the value at 1. So essentially, you can define the integral for arbitrary measures, and that kind of just works out. And again, like, this is something which you would develop over, like, the integral you would develop over maybe like 2 weeks of class. But it's really cool that this works in more generality. But for now, you can just imagine like the measure being the measure you're used to and everything working out nicely, and this d mu being a dx. Okay. Okay, so Now, actual claim. 1 over n k0. So let's say we define gn as 1 over n from k equals 0 to n minus 1 of f to the t to the k. So right, this is just one function. And what I claim is that if we have these conditions I showed you before, so if mu of t of b is equal to mu of b, meaning that your transformation preserves your measure. So again, if you try to imagine this as like a discrete time evolution, so let's say you have whatever water particle, water, and the water is moving around, and like your map describes for a given water molecule, where does it end up 1 second down the line, then this would kind of be an incompressibility condition, right? Because if you have like this spot of fluid and you look where it ends up 1 second later, then this tells you that the amount of volume is maintained. Okay. Second condition, egodicity. What do I mean by that? That is this condition that if b is equal to t of b, then mu of b equals 0, mu of b equals 1. This ensures that you don't have like silly simple systems, and it's sort of you can imagine it as a sort of mixing condition, though it's slightly cursed because mixing is also a technical term used for something slightly stronger, but well, right, if you, for example, just have circle rotation, then this wouldn't be satisfied, at least for like the normal measure where we just assign the area as the measure. So right here, like this inner circle gets mapped to itself by circle rotation. So you have something which is mapped to itself, but the measure is neither 0 nor 1, so this condition wouldn't be satisfied. So you need something which sort of shuffles around your points. Okay. Then limit n going to infinity of the integral of f d mu minus gn goes to 0. What is the norm on this space? Right, so this is just like how you write on vector norms. The norm is just equal to the difference squared. So this is equal to the integral over x of the integral of f d mu minus gn of x squared d mu. And this thing we claim goes to 0 as n goes to infinity. Okay. Yeah, I'm sorry. I feel like this might actually take a while to properly develop everything. But it's a fun proof. But I think we need to we need to go into a bit more technicalities than I maybe have hoped for to explain things properly. Okay. And right, it sort of makes sense that this is like, this also, right, this basically means that the difference also gets small pointwise. Actually translating it into a pointwise statement doesn't quite work, and perhaps I'll go into it in the end how you can kind of fix it, but that's a bit ugly. Okay. Good. Okay. The really cool thing about these square integrable functions is that they really do behave a lot like a vector space. And indeed, they form a vector space, and in particular, they form a vector space with an inner product, which is really cool. So you can define this thing, right? Okay, we can just forget about the complex conjugation and just do everything over the real numbers. Why make our life complicated? Okay, why do we need square integrability for that? Otherwise, this thing might actually not be well defined, because otherwise, this essentially you could have something that here goes to infinity, like the product of two functions for which, for example, the integral of the absolute value is finite needn't still have finite absolute value, a finite integral of absolute value. So it just turns out that for square integrable functions, this is like neat and well defined and everything makes sense. And also, like, the way to check that a function is square integrable is just to check that this is smaller than infinity, because this is exactly equal to the integral square, that the integral of the function squared. Okay, cool. And, well, it's a vector space, but it's an infinite dimensional vector space. So it turns out that, like, many of the things which you know from finite dimensional vector spaces still work. They do require some subtlety, and essentially you have to just develop much of the theory again from the ground up, and it just turns out that many things still work. Some things need new conditions. I'll just state the results there, but I hope that they'll make sense, because it's essentially like it feels the same way as with finite dimensions. Okay. In particular, what we can still do is projections. And what we claim is that even if let's for a second forget ergodicity, and we'll bring ergodicity back into the discussion at the end. So we just need the invariance. You can also keep it in the back of your head, but it's we won't need it for a couple of minutes. Okay, so claim. Oh no, claim is way too weak. Theorem by von Neumann. These GNs. Oh, okay. The inner product of the GNs to the whatever this means. So, okay, this is the inner product I described before. So this is just GN minus PTF, GN minus PTF, right? We just take the integral of the square again. That this thing goes to 0. And now the question is, what does this mean? This is the projection on the space of invariant functions. So the projection on the space of functions in L2 such that f composed with t is equal to f. Cool. Let's maybe give this a name. We now call this A. Cool. And okay, now let's just unravel right now what this means. Right, so this is in the case that T is new invariant. But needn't be ergodic. It's more general than that. However, if it is ergodic, then we get the entire claim we want. Because, well, this is a bit cursed. Can it be that the measure is ergodic and we get an invariant function? Turns out that is not possible. Why? Jesus Christ, I hope I'm going to manage this spontaneously. Okay. Okay, we look at the pre-image of any set under F. So we look at some subset of X, and we look at the pre-image of it under F, right? So the pre-image of B is equal to the pre-image under F composed with T of B, right? Because these are the same functions. This is equal to the pre-image of T of the pre-image of F. Just, yeah, I mean, think about it. Am I being silly? I don't think I'm being silly. That is correct, right? Yeah. Good. But hence, because T is a projection, we can just apply T on both sides. So we get that F minus 1 of B is equal to T of F minus 1 of B, which implies that the measure of F minus 1 of B is 0 or 1. Okay. Now, what does that mean? Well, let's say we can just start testing with intervals. And, right, let's say we have, let's say we get that, like, the interval from 0 to 10 has measure 1. Then the pre-image under F of the interval of 0 to 10 has measure minus 1. Then we can, like, look at these two intervals. Let's make it open here, 5, 10. And then, right, only one of those can then again have measure 1. Have pre-image under F with measure 1. Right? And perhaps I should elaborate. Right, because the what we had before, the sum. Okay, I didn't write this down. I erased it afterwards. That the measure adds itself up, right? Because the measure of F minus 1 of 0, 10, I hope not boring you, is equal to the measure of F minus 1 of 0, 5, disjoint union, and this like square thingy is a disjoint union from 5 to 10 is equal to mu of F minus 1 of 0, 5 disjoint union with F minus 1 of 5, 10. Okay, we quickly use that F minus 1 of A disjoint union B is equal to F minus 1 of A disjoint union F minus 1 of B. This is just a general fact about functions. This is always true. Just think about it. If you want, just pause the video and write everything down and it should make sense. It's just like manipulating symbols for maybe 2 minutes. Okay. And this, because these are two disjoint sets, should then be equal to the sum of the two plus mu of F minus 1 of 5, 10. So, because this is at a 0, this is at a 0, 1, this is at a 0, 1, and this is at a 0, 1. Exactly one of those two must be 0 and 0, 1. And, well, right, we can just like test this for different numbers, and for one pair of numbers it needs to be 1 because, well, the preimage of like all the real numbers must be 1, right? Otherwise that like doesn't make sense, right? Because the preimage of the entire space must be the entire space, because every set, every point in X is mapped to some point in the real numbers by F. Okay. And then we can just repeat this procedure and like get smaller and smaller intervals where the preimage is between 0 and 1. Is 1. And right, they're then like always contained in each other, and in the end you get that there's exactly one point which has preimage 1. And hence the function is constant. I hope that makes sense. F is constant. So actually, in the case that we have ergodicity, this space A here only consists of constant functions. And what then is projection on the space of constant functions? Well, a basis for the an orthonormal basis for the space of constant functions is just the function which is constantly 1 on the entire space. So the function which just sends x to 1. And it turns out that for these function spaces, projection still works pretty much the same as it does for not exactly the same. Pretty much the same as it does for finite dimensional vector spaces. So we can just project some function f onto our one orthonormal vector, and that is exactly the integral of f. Right, so this works the same, right? If you have infinite dimensions, right? If you have like whatever R3, so just 3-dimensional Euclidean space, and like you want to project onto some 2-dimensional plane, and you have 2 orthonormal vectors, say, then the projection of some of some vector v onto your space pt of v is just equal to E1 times v E1, so v in a product E1 plus E2 v in a product E2. And this is exactly what we're doing up here, right? Because like if we then multiply with this one function, then we get the function that is constantly equal to the integral of f to mu on the entire space. Okay, so the von Neumann-Ergodic theorem for ergodic T claims exactly what we want, because then this pt of f is equal to the integral of f, so we get that gn minus the integral of f d mu squared goes to 0, right, where gn are these partial sums, 0 to n minus 1 of f composed with theta to k. Cool. Okay, let's try to prove the von Neumann-Ergodic theorem. Okay. For that, we just define another space B, which is it's supposed to be the orthogonal complement of A. So G, again, square integrable. Again, why square integrable? Because square integrable functions are the functions which work nicely with the inner product space. If you want the actual terminology, the space of square integrable function forms a Hilbert space. And that is really, really cool, and it gives us like a ton of nice properties. And for example, it makes projections work, and like projections working is a really, really important property for space to have, which is also exactly the property which we're using right now. And it makes orthogonal complements work, which we also actively use. Okay, so claim the orthogonal complement of B is equal to A. Proof. Okay, so first we just pick some f in A and G minus GT, G composed with T in B. Then the inner product of F with G minus G composed with T is equal to, we just apply linearity, Fg minus F G composed with T is equal to F G minus, we just apply that F is equal to F composed with T, G composed with T. Okay. And now we do something relatively cool. Again, doing this rigorously would be slightly annoying and maybe take like 10 minutes. But this expression here equals F times G composed with T of X d mu integral over our entire space. But the point is that D maintains the measure. So essentially it puts different parts of the space to other points, to other points in the space, but it doesn't change how big they are. So it doesn't actually change the integral, right? If you for example have a rotation, right? Let's say you have R2 and you have some function which you integrate over R2, and you have the same function which you integrate over R2 and you first compose with, let's say, rotation by alpha. So you first rotate all of R2, let's say by whatever, 10 degrees. Then these two things are the same. It doesn't matter, right? If you flip the space around in such a way that the measure is maintained in such a way that the area is the same, then the integral can't really change, because you're essentially still integrating the function. You're just shuffling around where you integrate the things, but you're still integrating the exact same things, and you're integrating them with the same measure, essentially. Doing this rigorously is not super hard. It would just, like, in our lecture it was 5 minutes. It's just like right now not really properly possible, because like then I would need to define what this integral actually means rigorously, and I kind of don't want to do that. It's not ridiculously hard, but I feel like it would be kind of out of scope. Okay, so this is equal to the integral, just the integral of f times g over our entire space, which is just equal to the inner product. So this is equal to fg minus f inner product g, which is equal to 0. Okay, cool. That's nice, right? Because, well, if B is supposed to be if the orthogonal complement of B is supposed to be A, then, well, we better hope that vectors in A are also indeed orthogonal to B. Okay. So, perhaps this is a quick question to think about for yourself. Have you already proven the claim now? Okay, I'll quickly check whether the mic is working, otherwise I'll get very sad. Okay, the mic is working. Oh, only 35 minutes. We're being quick. Nice. Okay. No, indeed we have not proven the claim already. Why? Well, we've proven that every vector in A is indeed orthogonal to every vector in B, but perhaps there are vectors which are orthogonal to every vector in B, which are not in A. So assume that f is in L2, so f is square integrable, meaning that the integral of f is exists and is finite. The integral of f squared exists and is finite. And for every g in L2, f inner product with g composed with t is equal to 0. Okay. What does this mean? This means that f composed with g, f inner product g is equal to f inner product g composed with t. Okay. And now we do something funky. What is composition with t? Well, it turns out, right? No, actually, that actually very much makes sense, right? With what I explained to you here before, that if you compose with t on both sides, you get the inner product is maintained if you compose with t on both sides. So what that means is that if you have a square integrable function and you compose with t, you still get a square integrable function. So we can define ut as an operator on the space of square integrable functions, which takes a function g, on let's say a function h, and maps it to h composed with t. And this is well defined, as I just told you. So well defined as meaning that like it does indeed map every function in every square integral, every function where the integral of the square is finite to a function where the integral of the square is finite. Okay, so, and this is a linear map, right? Because if you take ut of alpha h plus whatever g, then that is by definition alpha h plus g composed with t, and that is equal to alpha h composed with t plus g composed with t is equal to alpha times ut of h plus ut of g. So this is actually a linear operator. So it's kind of a matrix. I mean, it kind of behaves like a matrix. But it's also kind of not, because it's infinite dimensional, so maybe lots of our theory breaks. But it turns out that it's a nice operator in the sense of it maintains norms, and for operators which are this nice or even like a little bit less nice, you can have, like if you have f utg, then you find a second operator such that we call this the adjoint operator, which flips it to an operator on the other side. And this is, okay, I don't know how much linear algebra you had, but you can do the exact same thing on finite dimensional vector spaces, where for any, let's say, xy in Rn, ax y is equal to x a transpose y. So in this case, for the finite dimensional case, this weird second operator is just equal to the transpose, right? Because, I mean, this is the exact same thing as saying that y ax is equal to a transpose y x. And this is the exact same thing like what we're doing up here. This, if you want to check this, you can just check this by checking against orthogonal vectors. So just if you're not familiar with this, this is called the adjoint, so that the transpose on real valued vector spaces, real valued finite dimensional vector spaces, the transpose of the matrix is just equal to the adjoint of the matrix. And the adjoint is this thing we call the adjoint this thing which like puts the linear operator on the other side of the inner product. And yeah, if you want, you can check that this works out by checking that it works out for this case, where E1, En are the canonical standard, let's say, standard orthonormal basis. Cis of R, Jesus Christ, Rn. Okay, this is incredibly ugly, Jesus. Rn. And if it works for the orthonormal basis, then it works for any vector, because any other vector you can represent as an inner product, as linear combinations of this orthonormal basis, and then you can just sum them up. You can put the sum into the inner product, because the inner product is linear, bilinear indeed, and then you get that it actually holds for all vectors in Rn. So once you get this, you quite quickly also get this for any xy in Rn. Cool. Okay, so now just trust me that this exists. Once you've built in finite dimensionals as well, and once you've built the proper theory, this is not like a super hard thing to prove. Not at all. Okay. So, okay, and note that if we do this, if you want to find out what the way to put it back, okay, I'll explain this when we get to it. Never mind. Okay, so going back, this means that f inner product G is equal to, right, f UTG, to use a new vocabulary, and this is equal to UT adjoint f inner product G for all G. Okay, but then we can pull this on the left hand side again, and we get that fg f minus ut star fg equals 0. But this is for all G in L2. So this also means that f minus, right, because ut star f is still in L2, is still a function which has integral, the square of the integral of the square being smaller than infinity. So everything is well defined. And we can just pick G equals f minus ut star f. And then we get this. And right, just by laws of the inner product, this is the norm of f minus ut star f. And if the norm of a vector is 0, then the vector is 0. So f minus ut star f equals 0, f is equal to ut star f. Okay, now we're almost where we want to be. What we actually want to have is that f is equal to utf is equal to f composed with t. But, well, is that also true? Well, let's just evaluate f minus utf squared. So this is f minus UTF, inner product f minus UTF. Right, the inner product, as we always define it, as just like the integral of f minus UTF in this case. Then we just expand. We get f squared from these two f terms. We get plus UTF norm squared plus f UTF, minus f UTF minus UTF f. Okay. But now we can just be clever again, right? We can apply what we know, namely that f UTF is equal to UT star f, and hence also UTF f is equal to f UT star f, right? Because UT star is exactly the operator that allows us to put UT on the other side, kind of. So we get f squared plus UT f squared minus UT star f minus f UT star f. Okay, I'll just I'll move this somewhere else such that it doesn't get in the way. Okay. Now, okay. We know that UT star we know that UT star f is equal to f by what we've seen before. So this is equal to f squared plus UTF squared minus 2 f squared, norm f squared. Okay, but what is UT norm of UTF squared? Well, this is just equal to f squared composed with t. And that, as I've explained before, right, because t just shifts around the space in such a way that like the measure is in the end still the same. This is equal to just the norm of f squared. So we actually get that this is equal to 2 norm f squared minus 2 norm f squared, which is equal to 0. So f is equal to UTF is equal to f composed with t, implying that f is in A. So indeed, if we have any element for which the square it has finite integral and it's orthonormal to all vectors in B, then it is in A. So now we've proven that the complement of B is equal to A. Okay. So, okay, lots of hard work for this one very compact line. Okay, now I hope you trust me on some, or okay, what if we apply the inner product again, the complement again? So, right, so we get that A complement, orthogonal complement of A is equal to orthogonal complement of B orthogonal complement. You've probably seen this. I hope you've seen orthogonal complements in your linear algebra course. But right, you would kind of just like to write B. But it turns out that this is not quite true in the context of infinite dimensional spaces. So what turns out to be the correct statement is B closure. So what happens? You might have a space which is a vector space, so a subvector space. So it is closed on addition and multiplication, but you might have points which you can get arbitrarily close to, but which are not contained in your space. So, right, if you have, let's say, R3, and you have R2, so let's say the plane as a subset of R3, then this doesn't really happen, right? It would be as if you had, like, let's say an open disk here, and there's some point right at the edge of the disk which is not contained. So with points in here, you can get arbitrarily close to that point, but it's not actually contained. So it's a bit weird that this happens in infinite dimensional spaces, but at the end of the day, you have to throw out some of your intuition for finite dimension of finite dimensional spaces and just be very happy that much of the theory still works. So yeah, closure turns out to be the correct thing. But what this means at the end of the day is just that we can take points arbitrarily close to the point which we actually want in B, and it turns out that everything is still completely fine. Okay. And also, right, let's perhaps try to build intuition by looking at the finite dimensional case a bit more. Why does it make sense if B were finite dimensional, that the orthogonal complement of B is equal to the orthogonal is equal to B, the orthogonal complement of the orthogonal complement is again equal to B if it's finite dimensional. Well, if it's finite dimensional, then we find a basis for B. Then we perform Gram-Schmidt. So I hope you've seen this. I think this, yeah, you probably have. Right, so any basis we can turn into an orthonormal basis. So we get an orthonormal basis of B. We can extend this to an orthonormal basis of the entire space. So whatever, let's perhaps write this down. So we get, let's say B is 5-dimensional, and like the entire space is 10-dimensional. Then we get like 5 orthonormal vectors in B, and another 5 orthonormal vectors outside of B, which together span the entire space. And then the complement is spanned by these vectors, right? Because anything that's in the span of the first 5 orthonormal vectors would be in B itself, and if it's a non-trivial linear combination of these first 5 orthonormal vectors, then the inner product, the norm would be positive, so you get like a you get that it's not actually orthonormal to every vector in B, so it's not in the orthogonal complement. And on the other hand, if you take any vector that is solely in the span of these last 5 orthogonal vectors, then, well, you can split up let's perhaps explicitly do this, right? If you have, let's say, 3 times E6 plus 5 times E7, then any vector in B we can write as a linear combination of vectors of these first orthonormal vectors. So let's say 2 E1 plus 3 E2. And then we can just split this up, right? So we get 2 E1 2 times 3 E1 E6 plus 3 times 5 E2 E7 and so on, right? There will be 4 terms, but all of these inner products are 0 because E1 to E10 form an orthonormal basis. Okay, I'll quickly pause the recording to check whether the background noises are audible because they're somewhat annoying for me.